Welcome to session 2. My name is Brad Wallin. I'm from Lawrence Livermore National Laboratory, and I manage nuclear threat reduction programs there. So if you have more questions about Livermore or that, I'm happy to talk to you later. As I understand it, I have two jobs. One is to introduce speakers, and the other is to keep people on time, so I'll do my best. So our first speaker is Walter Pettus. Got his PhD from the University of Wisconsin-Madison very recently. Explained to me that this is his last obligation for this program, so that's an important thing. His major was in experimental nuclear and particle physics. Advisor was Karsten Heeger. The practicum location, he worked at Lawrence Livermore National Laboratory, and his presentation title is Background Characterization and Detector Sensitivity in DM ice. So let's welcome Walter.
Well, thank you very much. So the presentation title has changed slightly from the abstract, but don't worry, I'll actually hit all of the science that the abstract covered too. So I'm going to switch gears a little bit from some of the other things you'll hear about this week to talking about dark matter and kind of astrophysics scale problems that we have. So if we want to understand the universe, one of the great ways to do it is to go out and observe it. And if you observe it in the visible light, you'll see one picture. And as you observe it in more ways, you can round out the picture and understand more about the astrophysics and the cosmology that's going on. So if you go to higher energy photons, you get yet a different image. And then if you go to your low energy photons, when you're measuring the cosmic microwave background, and you look out at the universe, you observe something which is incredibly isotropic and homogeneous. So this is isotropic to 1 part in 10 to the 4th. And what you're looking at in this diagram, the red are the hot spots and the blue are the cold spots. And so then you can do a correlation of the temperature in this image. And so if you plot out the power spectrum, it actually is an incredibly powerful probe of the cosmology underlying the evolution of the universe. And what this power spectrum can tell you is that there's a lot about the universe that we don't understand. Namely, everything that we know and understand is this 5% of the universe, the ordinary matter, and the other 95% is broken down into a very large chunk of dark matter, and then the dominant component, which is dark energy. Now, this doesn't just come from observations of the cosmic microwave background. There are a wealth of other cosmological observations which contribute to this, ranging anywhere from inferring the matter distribution in cluster mergers to galactic scale rotation curves. There's a lot of simulation that goes on behind this. So there's a very rich field of cosmology which is trying to pin down this picture, but what these observations are doing is they're telling you how much dark matter there is, but they're not telling you what that dark matter actually is. So that's what my experiment is hoping to do. And we're just one part of a large puzzle. So if you're trying to identify what this dark matter is in the universe, there are 3 main ways you can do it. You can either try and make it directly. Collider searches like the Large Hadron Collider do that. You can look for its indirect signatures from annihilation or decay. Experiments like the Fermi Space Telescope are doing that through NASA. And then there are these direct searches, which are trying to measure dark matter interactions with a detector that we have in our lab. So narrowing in on the direct searches and taking, just as a case study, one of the most common ones in the field, the DOMA detector. What makes a good dark matter detector? Well, you need to scale these up to be very large in mass because your sensitivity will scale with detector mass. So for DOMA, they have a 250 kilogram array of sodium iodide crystal. It's a very old detector technology, but it's come back to the fore. And because you can't get one detector which is of enough mass, you start to put together an array of them, which also gives you an additional important handle, because if you're trying to put 2 very sensitive detectors next to each other, then you can constrain the backgrounds of the detectors based on the correlations between them. And we're trying to look for a very rare signal. So we make our detectors out of incredibly radio-pure materials to control our backgrounds. And because we're working close to our threshold, we try and control everything about the environment, make sure there's nothing fluctuating, make sure there's not backgrounds coming in. So if you look at the spectrum that these detectors are measuring, it's going to look something like this. You're pushing down your energy threshold to the level of few to sub-keV energies. And you really need that detector threshold to be as low as possible in order to characterize the exponential noises which are sneaking in. Because if you don't understand your detector, then you're not going to understand the signal that you're measuring. So for this particular detector, the relevant figure of merit in their background is 1 in these counts per day per kilogram per keV units, or DRU, that I'll come back to as our goal point for our experiment. Now, the reason I signaled out the DAMA experiment is because they're actually unique in the dark matter field. They're the only ones who have actually claimed to have detected dark matter, and they've done it to incredible statistical significance. Over a 15-year period, they've measured a consistent annual modulation, and that annual modulation is one of the smoking gun signatures that we expect for dark matter, because as the Earth moves around the sun and the sun moves around the center of the galaxy, you expect that our velocity relative to the dark matter will be changing. So that's going to give rise to this characteristic modulation, which is a way that you can know that what you're seeing is a signal and not a background. So this should be very compelling and very great because it means we found dark matter. Except that that's not the whole picture, because one experiment is claimed to have found it, but every other experiment which is run has, at this point, come up with a null result. So this plot on the right is a little busy, but what you need to know is that these green bubbles are what DAMA claims their dark matter should look like in some mass versus cross-section parameter space. And all of these bands, these lines, are saying that they've excluded any dark matter which would be up in this region. So it's not just a single experiment which has said DAMA can't be the right explanation. It's numerous detectors, numerous different detector technologies, numerous targets. So there's something very strange going on in this picture. Either we don't understand the physics behind it, the astrophysics, the particle physics of the interaction, or there's something that we don't understand fundamentally about our detectors, an instrumental effect or a background that we haven't accounted for. So that's where the DMICE set of experiments come in, and that's what I've spent the last 4 years working on, is trying to build more sensitive detectors and trying to characterize them so that we really understand their response and what we measure we can trust. So the bulk of my thesis analysis has been devoted to the experiment on the left, DMICE 17. That's been running since right around when I joined the fellowship. And then more recently, we've done some R&D work building towards what you have on the right, which is a detector which is capable of unambiguously testing this DAMA signal claim. Okay, so DMICE, what's the ICE part of it? And so if you look at the world of where dark matter experiments are running, there's a lot of different experiments, which is why there are a lot of lines on that previous plot. But if you think about the experiment we want to test is DAMA, and they measured a modulating signal. So we want to make sure that there's nothing coming through on a year timescale which is modulating with the seasons. So we'd actually like to simplify the site selection to only restrict it to southern hemisphere sites, which made our choice rather easy. So there are a couple of planned labs, but if you want a facility that already exists, you have to go to the South Pole. So that motivated our site selection. So the DMICE 17 experiment, what have we actually done? What does it look like? So there are a pair of detectors, and if you're from the astrophysics community, you'll know that there's also a neutrino observatory at the South Pole that has instrumented a cubic kilometer of ice. We're deployed in and under them at the bottom of 2 of their strings. So the ice is close to 3 kilometers thick at the South Pole, and we're deployed at a depth of 2450 meters. So some of the things that we wanted to prove with the DMICE 17 detectors that I'll highlight in this talk, first of all, that you could do this, that you could sync your rare event search detector in the ice and actually run it stably and understand it over a multiple year period. We wanted to know that the environment was stable enough that you could take the data and understand it. We wanted to understand the backgrounds in this environment and what you could tell about sources of background specifically from muons, which are a common candidate that's known to modulate through the year. So for those of you who aren't familiar with the South Pole and the science that gets done there, there's an NSF-run station. Am I allowed to say that here? So they provide the infrastructure for the science there. There's a suite of astrophysics and cosmology experiments that go on out in the dark sector. So a couple of CMB experiments, Keck bicep 3 SPT, as well as cosmic rays and neutrinos. And then we added direct detection dark matter. And then there's also climate modeling and seismic science. So there's a lot of really interesting science which is being driven at the South Pole. Now, it's not exactly the easiest place to go and do research. Everything you do there has to be flown in on a plane, and it's only that plane which flies in, so it has to fit on that plane. Once you get there, there aren't roads, there aren't overhead cranes everywhere, so there's lots of heavy machinery. If you want to drill down to 2.5 kilometers, that's quite an undertaking. It takes 10 train-sized crates to provide all of the water heating and pressure to power the drill, kilometers worth of cable to drill that deep. And then this is a picture of the drill head. There's lots of complicated diagnostics and high-pressure jets to get the holes to drill down that deep. And then at the end, you get to lower your detector into a hole and hope it turns on at the other end. So this was my title slide. This is one of the DMI-17 detectors. You can see it's going down about 30 to 50 meters before it hits the water, and then it'll be in water and get permanently encased in ice once all of the detectors on this string are deployed. So we did this, great, we turned it on, it worked. What does it mean in terms of uptime and stability for a detector running at the South Pole? Well, it's a pretty quiet environment. You're not likely to go down there and mess with your detector, so it means you get great uptime. I've been running the detectors over the last 4 years, so I'm pretty happy that we have 99% uptime. That's a lot of statistics and a lot of data to analyze, and we understand where we've lost our downtime. In terms of temperature stability, the South Pole ice is a great place to do it because you're in the middle of a gigaton of ice, so that's a lot of thermal insulation once you equilibrate to your temperature. So there's lots of cooling at the beginning, but then you enter a pretty constant temperature regime, which means your crystal response isn't going to change. And then in terms of the total detector backgrounds, before we deployed, we were able to make radioassays of all the detector components and build a pretty robust detector background model so that we can understand our energy scale and what backgrounds go into that. So then the hard types of backgrounds. Because it's not all just the intrinsics that are in your detector components, you have to worry about cosmic rays. So for those of you who don't think about cosmic rays all the time, you have these high energy particles coming from mostly beyond the solar system. They strike the upper atmosphere, and they interact with the air molecules, and they create these showers. And for the things that you have to worry about in these showers, you can get pion production, which decays into muons. Muons are going to be very penetrating and go very deep, so that's why we put all of our detectors deep underground. There's also an electromagnetic shower component, which is one of the things that's harnessed for the surface cosmic ray detectors. And then there's also a hadronic component where a cosmic ray that strikes a nucleus, it's going to blast out the protons and neutrons in there. And we're going to have to worry about those for the purposes of activation. So this is a very simplified picture of a shower. If you actually simulate it rigorously, you can have thousands or millions of particles that you have to worry about. So what do these particles do to our detector? So the first thing that's well known is you can have a muon which penetrates very deep. Our detectors are down here underneath the ice cube. So we can track these muons very well, which is useful for our detector because it means that we can unambiguously tag when a muon passes through our detector. Now, one of the things that's of concern for a low background experiment is you're looking for few keV signals. Okay, these muons aren't that signal. They're going to be tens of MeV. They're going to be the most energetic particles you measure. But if you deposit that much energy into your crystal, you can have long-lived, very low energy signals which accompany them. So the fact that we can tag muons, we actually know something about their energy because of all of this tracking of IceCube above us, is very useful for us. And then we can look at the decay. So there's a seconds-long period of decay for these in-ice crystals where you're getting sub-keV events, but you have to understand your detector response at the low energy region in order to make sure that you're not reconstructing them to higher energies. So this is one of the really interesting things which has come out of the in-ice detectors. And the second thing, which I mentioned, which my abstract kind of harped on, I'm finally getting to it, is cosmogenic activation. So this isn't something you have to worry about so much after your detectors are deployed, but when you're getting them to the South Pole, you're putting them into a very high hadronic cosmic ray flux. So you can have, say, a neutron come in, blast one of your target nuclei, talking about sodium iodide, so I-127 is one of the major drivers of the activation products, and comes in with really high energy, blasts out a couple other neutrons, and you're left with a different state of iodine. So in this case, I-125 is radioactive. It's got a 60-day half-life. And then all of a sudden, all of your care in building your detector out of radiopure materials is kind of for naught because you've created radioactive backgrounds in your detector after you built it. So that's annoying. And then so this is sort of a few neutron emission. You can also have much harder impacts where you blow out more nucleons and end up further from your starting nucleus. So the things that you have to think about when you're considering cosmogenic activation, first of all, the neutrons are what dominates, and that's mostly just because of the interaction length of a proton. There aren't as many of them in the cosmic ray fluxes. The types of energies that we're interested in for cosmic rays are 10 to 100 MeV, just because that's where the interaction rates are peaked. Although higher energies also contribute as well, lower energies typically don't have the energy to knock out the nucleons. And then you have to worry about the fact that everywhere you are on the globe and every altitude that you're thinking about is going to have a different cosmic ray flux. So there's an approximately exponential dependence on altitude, and then the positional dependence is much harder. It relates to the Earth's magnetic field providing shielding. There are equations to model this, but in general you can have up to a factor of 5 difference depending on where you are on the Earth for the same altitude in what your cosmic ray flux looks like. So for a detector like DMI-17, we have sort of an unusual set of challenges. Usually you build these detectors underground, and if you are moving components overground, you do it in shielding containers and you keep them at sea level. But we're going to the South Pole, and I already told you that you have to fly your detectors down there. And in fact, we picked up a couple of extra flight segments because of the timescale for deploying DMI-17. So when you're thinking about your flights and what that does to your cosmogenic activation, you pick up a couple of orders of magnitude in terms of an elevated rate of your neutron flux or correspondingly your cosmogenic activation rate. So we had to build all of this into our model in order to account for what the expected cosmogenic activation rate was. And then briefly what I'm showing here, you can think either in terms of the scaling factor which you have to apply to your activation rate. So you get punctuated points where you're flying your detectors, and then the long flat segments are storage. Here you can see at the South Pole, because it's at altitude, you're a little over a factor of 10 increase. Or you can think of it in terms, because it's a cumulative activation where you're integrating over time, just integrating this same plot. And so you see that the flights are about half of the activation, but there's also significant activation periods that you can have built in just based on keeping your detectors at sea level for a while. So these are things you have to worry about. And in terms of understanding how the scalings work, it's useful to look at the flight segments. So not all flights are equal. These are all polar latitude flights, whereas this is the one which goes across the equator. So you get this factor of 5 to 6 suppression. And then one of the polar flights is lower altitude, and so just flying your airplane, doing your cargo movement at a different altitude can give you an improvement of a factor of 2 to 3 in the activation rate. So then this is still a simplified model because for every isotope that you're interested in, you have to build in decay rates. And for the purposes of DMI-17, we were interested in about 20 different isotopes that we had to model. So what goes into all of these models? You take the known activation rates at sea level, you scale them appropriately, and then you can build them into your detector Monte Carlo to see what that means in terms of the rates that you expect in your detector. So the crystal components dominate across most of the energy region, and when you're getting down into the low energy region of interest, remember we're interested in sort of few keV level signals. Again, that's going to be the crystal components that drive it, but you can see, so the components are broken out by color, and for instance, the green one, which is the dominant at low energy, you can constrain that from higher energy features in the spectrum. So for DMI-17, we actually don't have the sensitivity at low energy yet. It's demonstrating the feasibility for a future experiment. So I'm not analyzing the actual region of interest for a dark matter search, but what you see here clearly over the first few months of data are the same features that were popping out in the simulation. So you expect a dominant peak at 65 keV and then a couple other lower energy peaks. This one you're not going to see because it's of the half-life and the months that I'm showing. So you see this split peak structure at low energy, and then the dominant peak. So that's the first way that you can verify that you actually understand the spectral features that you're seeing, is that it's matching your simulation expectation. And then the second handle that you have on it is you can map out the decay half-life of these peaks over time and make sure that it matches your literature values. So this is very important for an experiment like DMICE, which is deployed without any calibration sources, that even if there was something that we didn't understand about our full energy spectrum, we have these calibration points that we know beyond ambiguity what isotopes they correspond to. So without getting bogged down in the details, the simulation can reproduce all the features. There's a couple of interesting things that came out of this. It gave us a better understanding of our full detector background because there were a couple of components that we had already built into the background model, but were actually decaying away. So it gave us an independent handle on those. And then all of the features were represented after including the cosmogenic features, with the one interesting note that the energy resolution that we had been quoting was a slight overestimate, so we actually had better energy resolution than we had been quoting, which was great. So then if you sort of think about the summary of the science that we got out in terms of cosmogenic activation, compared to the one other experiment which has done a similar measurement, we saw all of the activation products that we expected. The ones that we didn't see weren't accessible for our detectors because we didn't start taking data soon enough, or this one required a multi-crystal veto. There's only one instance where we actually measured a different value that we're still trying to trace down the source of error on that and figure out if it's in their analysis or ours. So DMI-17 was sort of this pathfinder experiment to demonstrate that you can do it. And it was very successful in terms of achieving all the experimental goals that we had in mind. So then that makes you start thinking ahead to the next phase of the experiment and doing this test and finding out really what's going on with the dark matter field. So our proposal is this packed array that's similar to how the DAMA experiment had designed theirs. They also had a packed array 5 by 5. Ours is constrained by how big a hole you can drill in the ice. And if you really want to understand your backgrounds, you want to run in both hemispheres. So we're talking about running the same detectors both in the north and the south. Now, we've learned a lot of things over the years, which have enabled us, we've gotten cleaner components to build our detectors out of. And then based on the background measurements that we have from in ice, we can build a pretty robust background model for what we expect our full-scale backgrounds to be. So the DAMA experiment had backgrounds of around 1 in these DRU units. So we're projecting a slightly higher background level for what we know we can do right now. But this is very promising. And the background features at low energy are dominated by the crystals. So it's determined by how well our crystal growers can do at limiting their backgrounds. There's this peak here from potassium-40, which is really irritating. It's right in our region of interest. And then there's a flat background from lead-210, radon daughter. So then if we think about what cosmogenic activation is going to do to the next phase of the experiment, we'll have more flexibility, we'll have more time to plan and make sure that we do it right, but there's still some limitations that you're built in. You're still going to fly your detectors to pole. That's still going to give you that elevated activation rate. But previously, we flew components from the vendors in Europe and down to New Zealand. We can take those trips by ship. We can talk about limiting time at the South Pole. So just based on a couple of quick estimates of what happens if you remove these early flight stages, those take out about 20% of the total activation. Removing the South Pole time, it's another slightly under 20% of your total activation. So what does that mean about your activation background on top of the other intrinsics that I already showed? So we're, again, interested in this low energy region, but I've shown up to a couple hundred keV because that's, we can constrain our backgrounds at those energies. So at deployment, you have quite high rates, but your fastest decay product has a 13-day half-life. So really, over the course of your experiment, you're worried about an 100-day half-life decay product and this sort of 1 DRU level background that your cosmogenics are going to add. You can think about further decreasing the cosmogenic activation. So where does the activation that leads to those come from? And this is singling out just the component in green, which is going to dominate over the experimental lifetime. It's still one of their polar flight segments and your South Pole time. So we've done studies on what you can do in terms of flying at lower altitude. Or when I went to pole a couple years ago, I took a cosmic ray detector with me and measured some storage locations, which give us more flexibility in decreasing this chunk of the pie. So I'll drive to wrap up. What can you do with these types of backgrounds of the sort of 2 to 3 DRU level? So 2 is at the green level on these curves. So if you assume that DAMA measured something real that we can measure, then you want some sort of 5 sigma test of their experiment. You can achieve that within 2 years of running at 2 DRU background. If you assume that we're not going to see what they saw, you want to have a strong exclusion to their parameter space. So here their bubbles have been drawn in black. And again, the green curve shows you what kind of sensitivity we're going to have. So there's a really strong test that we can do of the DAMA result. So I'll wrap up with just a couple of summaries. It's been a really fun and exciting time to work in dark matter. A couple of papers that we've already put out, which were highlighted earlier in the talk. And then the reason I'm postdocing with Karsten still is we're trying to grind out 4 more papers to complete the analysis set of DMICE. Now, what I hope I've left you with is that sodium iodide actually has a really important role to play in understanding the dark matter signal, and DMICE 250 is really uniquely poised because of its southern hemisphere location. And I've had a lot of fun building detectors, taking them apart, rebuilding them. Less fun moving all the lead for the castles. It turns out metric tons of lead is just not fun to move. And playing a lot of Frisbee, including at the South Pole. So I want to thank Krell for making this fellowship possible, for the NNSA for their funding, and to all of you for listening.